Good afternoon, everybody. My name's Alastair. I'm a business development manager at NVIDIA. First of all, I'd like to thank NetApp for inviting NVIDIA along this afternoon. I want to talk for about 15 minutes and then pass across to Steve over here and talk about our joint technology. I hope you like the video. It was shown last week at our GTC conference in San Jose, California. It was kicked off our keynote presentation by our CEO. And it kind of gives a great perspective, I think, on where NVIDIA is going as a company. Our heritage has been graphics, but now we're very much an artificial intelligence company, infrastructure company. And that's really what I wanted to talk about briefly with you today, just give you an overview from a financial services perspective of what we're seeing in the marketplace. And then open up to Steve and why our two companies have come together to adopt a reference architecture. First of all, what I'd like to do, I'll jump onto the second slide, is just level set with everyone in terms of who NVIDIA are. Many of you will recognize the name. We're a graphics card that sits in your laptop PC and exhilarates these wonderful games that you play up in your bedroom, or your kids play up in their bedroom, spotty teenagers, a few bald-headed dads perhaps as well. The heritage of NVIDIA, we're a 25-year-old company, was absolutely in the consumer graphics space, delivering what is our core technology, a GPU, a graphical processing unit, a chip that offloaded the graphics pixel generation and fire those pixels up 60 times a second onto a screen to give that great visual gaming experience. And we sell tens of millions of these cards every year to the sort of people I've just mentioned. They're a very, very successful business, still represents 40–50% of our business. But I'm very pleased to say we've been able to innovate and scale around that core technology. And it was about 10 years ago that research scientists and in laboratories started to think about how they could leverage these lightweight computational cores, of which there were hundreds in those days, but now there are thousands on a single die. And how they could leverage that to improve the performance of their simulations. Because fundamentally, a GPU is a parallel processing card. It doesn't do sequential computing, it does parallel computation, hence firing up pixels, thousands of them, onto a screen, 60 times a second. And so these researchers started looking at GPU computing as a way of being able to do better science and faster simulation. And that spawned a very significant business for us in the high-performance computing world. GPUs, thousands of GPUs sit inside the largest supercomputers in the world. We've also had success in a number of vertical markets, oil and gas and defense. And one that's close to my heart, and no doubt yours, in the space of financial services. And we've over the last few years been successful in selling a lot of GPUs into many of the large investment banks to perform their market risk and counterparty risk. It was alluded to a little bit earlier on. Over the last 3 or 4 years, however, that parallel processing capability serendipitously has come together with the massive expansion in data that we see in the world to provide a springboard for perhaps the most powerful form of artificial intelligence. Machine learning is widespread and used in many of the banks and insurance companies, but it's deep learning, or if you like, neural networks, which arguably delivers the most capable accuracy, most highest accuracy in the space of artificial intelligence. And as a consequence, NVIDIA is seen as a sort of go-to chip for accelerating neural networks. And we've seen a massive takeoff in the hyperscale community, the Apples, the Googles, the Facebooks, the Baidus, the Tencents, in their analytics on big data that is sent to them by ourselves and our children, uploading text and photographs, images, video, and the like. So Artificial intelligence, I'm specifically talking about deep learning here, the application of neural networks. As I say, significant in the hyperscale community. They're all these large firms, Facebook and Google, doing neural network training, which is our strength, the training of large data to be able to deliver back services to you in the form of facial recognition, in terms of recommendation systems, speech translation, and so forth. All of that is being done on neural networks. And we're beginning to see the adoption of neural networks in the enterprise space as well. Perhaps the leading markets at the moment for us are in the automobile industry. We all read about, and perhaps slightly scared by the concept of self-driving cars. All of that is being based on neural networks, the training of neural networks, and then inferring those highly accurate models into the car in order to be able to take us safely from A to B. The other big area, big growth area for us is in the health space. Diagnostics, imagery, and being able to, machines now outperforming oncologists and radiologists in the detection of cancer cells, and of course being able to do it at scale at a much greater pace than the human being. These are some of the other industries we're kind of playing in. They're coming along. Financial services is a growth market for us. We think it's going to be very big, and a little bit later on I'll allude to some of the early use cases that we've been seeing. Now, neural networks are not a new invention. They've been around for 40, 50 years, but they rely very heavily on very large amounts of data and a lot of computational power. I've got a slide later on which kind of takes you through the workflow or the algorithm. But fundamentally, this blue line here, small neural network, couldn't keep pace with the machine learning techniques, the more statistical regression and cluster type analytics in terms of unable to deliver that accuracy. But we've had this coming together over the last few years. We've probably all seen a version of this slide. The availability of data from sensor data, from internet data, social media data, converging on data scientists becoming a lot more creative and innovative in their use of neural networks. We've seen a number of derivative types of neural network developing. And then cheap computational power. The training of neural networks can take weeks, certainly days, if not weeks of time on traditional CPU architecture. But a GPU accelerator, which is parallel in nature and matches directly onto the computation of the training of that neural network, has enabled data scientists to get easy access to effectively a supercomputer on their desk-side PC, and to be able to bring down training times from weeks to days to hours, and therefore being able to iterate more quickly and get to time to market advantage. It's all started around 2012. Many of you may have heard of a public competition called Imagenet, 1.2 million labeled images. Previous to 2012, data scientists, computer vision engineers would handcraft feature engineering to try and identify the bill on that bird or the paw on that dog, and hand crank code. And they got, on average, about 75% accuracy. There's a guy called Alastair in 2012, got a $500 GPU card, consumer card, and ran a neural network through the Imagenet database, and immediately improved accuracy by 10%, up to 85%. And over the next few years, the Googles, the Facebooks, and others have piled into this competition. And we're now getting accuracy which outperforms human beings to a degree, well, something like 95, 96%. And this is based on very large data sets and very considerable computational power. And the market has really taken off since that time. We're now seeing neural networks outperform more traditional machine learning techniques. Big NN up there, very high accuracy. And that's what's driving this hyperscaler interest. It's now driving the interest of the enterprise. Data scientists want ever more accuracy. This is the kind of the workflow of a neural network. It's labeled data here, image of a cat, label, likewise with the others, propagating that data forward and backwards through a neural network hundreds, if not tens of thousands of times in order to improve the weighting and ultimately arriving at a trained model with hopefully very high degree of accuracy. If you get up at 95, 96%, you may feel confident about putting that into a production inference environment where you trim that model and then put it out in the field on a smartphone, possibly even in a data center, in a robot, in a self-driving car, and away it goes. So moving quickly on, these are the sorts of questions that neural nets can answer. And these are some examples of the industries, some traditional possible use cases. I've got a couple here in the area of prediction, sentiment analysis, and fraud detection that we'll move on to quickly. This was a presentation given at one of our technology conferences, I think in 2018. Triumph, our Canadian asset manager, and they wanted to do sentiment analysis on the tens of thousands of newswire feeds that come out daily across the business sector. They've got a limited pool of investment analysts. They want to be able to try and identify alpha, try and spot signals that might move the market. And they had 76% under proof of concept environment, 76% accuracy on a natural language processing neural network, which took in these newswire feeds daily, tried to detect the stock's ticker symbol, the sentiment quotient in terms of positive, neutral, or negative, and then some indication of the possible implication in terms of a stock price. And we're seeing other big vendors, Bloomberg are doing a similar sort of thing with Twitter feeds. State Street Bank are offering a service to their banking customers. Ravenpack, a European software vendor, offering a service based on this type of concept. And then in the fraud detection credit card space, PayPal, who've been using machine learning techniques for many years, now adopting deep learning in the form of neural networks. I believe they're using GPUs. Traditional fraud detection is based around simple rules-based engine, but they are quite crude and can miss out on non-linear relationships that neural nets can pick up in terms of a multitude of different type of variables and being able to spot unusual patterns. And importantly for PayPal, they've been able to dramatically reduce their false positive rate, reduce the human beings involved in some of those investigations. I apologize for the product slide, but I mean, NVIDIA is massively innovating in our technology. It's not just the hardware, but the point I just want to briefly touch on is in the software stack. We're not just simply a hardware processor company. We are building a container-based repository in the cloud, which can be accessed in the cloud or down on an on-prem device that addresses the challenge of open source software in terms of integrating it all together. It's the bane of the data scientist's life is pulling down the various open version of TensorFlow and then linking that with a version of Linux and then linking that to a driver of one form or another. And we take this headache away. We call it NGC. NVIDIA GPU Cloud. It's a repository out there. You sign up for it. It's freely downloadable. And these containers have GPU optimized capability. So we optimize. We have a group of engineers across the 8 different framework vendors optimizing their frameworks for GPU together with a bunch of the libraries and the various other components needed for a deep learning network. So that in one slide is, if you like, the the platform, our hardware, and then here's the third-party frameworks. So all highly engineered to deliver maximum efficiency. We've even developed our own NVIDIA appliance for deep learning, DGX-1, and that's going well. But I guess what I'd like to do is segue now to Steve. NetApp and NVIDIA over the last, I guess, year or so have come together, and we've defined a reference architecture, because the fundamental challenge here is massive amounts of data. This is a car example. I mentioned the self-driving cars. All the big German auto companies massively investing in this space. They're sending fleets of cars out, collecting video imagery of as they drive along. Autonomous vehicle picking up 1 terabyte per hour of video, which is then has to go into a neural network to be trained in order to be able to get a highly optimal and accurate model. Training sets, you can see the sorts of numbers there. And a GPU is a very hungry device. It needs to be fed with data incessantly and at a very high volume. And traditional storage just simply doesn't work. And we're very pleased that we've come together with NetApp to deliver an architecture. That's a picture of a box. We won't dwell on that, I suspect, for too long, Steve. But it's actually a pod. We call it a pod. There's a bunch of our DGX boxes there and a NetApp box above it. And that enables very high-end deep learning data scientist groups and infrastructure groups to be able to deliver time to market in developing their training models. So do we want to have a couple of questions before we pass across?
At this stage?
Yeah. I apologise, I've kind of rattled through it a little bit, but...
Yeah, a question about regulation and how it's applied to deep learning as opposed to some of the machine learning. The machine stuff, if I had to, I could go through it with a pad and paper and prove to the regulation.
Yeah.
The neural stuff, not so much, and I'm just curious if you have any idea where it's moving, how fast?
Yeah, I mean, you raise a very valid objection to neural networks in the financial services space and possibly some others, in the fact that it's effectively a black box. And a raw neural network won't tell you the parameters and the final weights, and regulators don't like that. They're like a deterministic solution. And so for the certain classes of application where it may be deep learning is not appropriate, but for other areas it certainly is the case. And relevant and being applied in practice. There are software companies looking at the whole explainability issue.